what did we say about checking the proportional hazard assumption? Well, first thing, talking about the proportional hazard assumption, we're talking about the Cox model, which we spent a couple of classes ago introducing what the model looked like, called the Cox proportional hazards model. There's an assumption called proportional hazards that basically can be stated in a number of ways, but one way to state it is that the hazard ratio is constant over time. That's what you mean by the proportional hazard assumption being satisfied. Another way of saying that is that you can get one hazard from another hazard by multiplying it by a constant or a number that is independent of time. So then we spent the last class talking about checking the proportional hazard assumption. How can you determine whether it's okay to use this model? And basically, we talked about three approaches. A graphical approach, and there are actually two alternative versions of the graphical approach, and the one we focused on, and the only one you're going to be asked about on the exam, if at all, is going to be the log-log approach, where you have to look at log-log curves to determine whether they're parallel or not. That's one approach. Another approach is what's called a time-dependent variable approach, where you wind up adding to your model a product term involving one of your time-independent variables with some function of time. And then you have to work through this extended Cox model in order to decide whether this extra variable that you've added is significant or not. And basically, I'm not really going to ask any questions about how to do that, per se, how you actually fit that model and get estimates of that model, because that's something we'll be talking about on Tuesday of next week after the exam is over. But I do want you to know that this is an approach. This is one of the alternative approaches. And so there could be a question on that. I'm not saying there is or there isn't, on this being one of the alternative approaches. And then there's a third approach, which I spent a little bit of time, but not as much as I could have spent, approach for checking the proportional hazard assumption, which is called the goodness of fit approach. And these are the three approaches that you could use. And as I said on this slide, the first slide in this presentation here, is that these three approaches have advantages and disadvantages. And if we talk about the graphical approach, which we looked at some examples. We're looking at log-log curves to see whether they're parallel or not. A key issue there is how parallel is parallel. How do you decide that? And that's a subjective decision, and different people, different groups of people or different people might make different conclusions, so that's drawback. That's a drawback to it, but it is one of the ways to evaluate the proportional hazard assumption. Another problem with the log-log survival curve approach, that graphical approach, is that if you have several variables you want to evaluate whether they satisfy the proportional hazard assumption or not, how do you do that? What strategy to use to do that? And when I talked about it, when I gave you some when I went through this thing and gave you some examples, I'm just going really fast. I showed you some log-log curves. For the remission time example, what I showed you first was what would happen if you looked at each one of these variables, treatment type, log white blood cell count, and sex, separately to see whether they separately satisfy the proportional hazard assumption by looking at log-log curves. And of course, again, looking at this log-log graph for the log white blood cell count, you saw that, well, is it parallel or isn't it parallel? And it's not that easy to determine and not that easy to decide. And the rough rule that people use is how badly non-parallel it is. But then again, that still leaves a lot of people room for making judgment. So that's a drawback. And of course, the other drawback is if you have three variables, like log white blood cell count, treatment, and sex, and you look at these things one at a time, and you make a decision, like in this case, the sex variable doesn't look like it satisfies the assumption because the curves are crossing here. The log-log curves are crossing, definitely not parallel. Then you might say, well, since two of them satisfied the assumption and the third one, or more or less, this one certainly did, this one more or less did, this one probably didn't, what do I do next? Do I just make that as my final decision and say that, okay, as far as the graphical part, not the other parts yet, as far as the graphical part, the log-log curve is not, the sex variable doesn't satisfy the assumption. And then I say, okay, I'll go on with my analysis and assume that. Well, problem is you've only looked at these variables one at a time. So what can you do in addition to looking at them one at a time? Well, what you could do is say, well, I've decided that treatment certainly is okay, satisfying the assumption if I look at them one at a time, and log white blood cell count is more or less okay. Maybe what I should do is say, let's put them in the model, and then the variable that I'm really worried about, let's leave that out of the model and assess whether that variable satisfies the assumption given the variables that look like they already do. So that's another part of a strategy that you have to use sort of to evaluate the proportional hazard assumption, even when you're talking about the graphical way of doing it. So it's not just looking at them one at a time, it's doing it something sequentially, looking at them one at a time, making a decision from one at a time, what to put in and what to leave out, and then to keep sequentially adding something in if it looks like adding a variable in as satisfying the assumption, if it looks like as you're going sequentially through, something is doing okay and something necessarily isn't, so you keep leaving it out. So that's another sort of difficulty with the log-log approach, with the graphical approach, which actually is a difficulty even when you're talking about the other approach, any of the other two approaches. The time-dependent variable approach, again, which we're going to go into more detail starting next week, has one of the problems is how do you do that one variable at a time, or what strategy do you use? That applies to that situation, applies to that approach, and even the other approach, the goodness of fit approach. Another problem with the time-dependent variable approach is what function of time do you put in? Is it exposure, treatment times the log of time? What product term do you put in? So that's a questionable thing you also have to decide. We'll wrestle with that when we start talking about that next week. And for the goodness of fit approach, which I briefly showed you somewhere or other, now where am I? Let's see where I am here. Maybe I have to go backwards here. Go backwards. Yeah, I do have to go back. Yeah. I showed you this. Remember this slide? Now, of course, you have to find, well, where's the slide? It's slide number 17 in that PowerPoint presentation. But what does this slide say? Well, what this slide does is it looks at that goodness of fit approach, which I didn't get into the details of how it works. I just showed you what the output is. If you go through the process of using a computer code and carrying out and getting the information you need to make a decision. And in this particular case, the three variables, treatment, log white blood cell count, and sex, were all put in the model, and then a certain computer approach was taken, a certain computer code, and SAS was used to come up with some p-values. And these p-values turn out to be, they actually turn out to be ranks in some form, but turn out to be p-values that you would use to decide whether a variable is significant or not. And as we saw last time, maybe we did this fast, but as we saw last time, the p-value for the sex variable is pretty significant at the 5% level, and the p-values for the other two variables aren't significant, right? So it looks like when you use the goodness of fit approach, you get almost the same conclusion. You get essentially the same conclusion as you would get if you use the log-log approach, that sex doesn't satisfy the assumption, and the treatment variable and the log white blood cell variables do. Now, again, a drawback with what I'm showing you here is that I put those three variables in the model all together. Maybe I should have done them separately before putting them in the model. That's a better approach, doing them one at a time before you start adding variables that look like they're good given other ones that may not be good. So anyhow, this is there is this issue when you're doing these three checks of these three ways to check the proportional hazard assumption, that you have to think about how you're going to, the process that you're going to use, and it really should be sequential. First start with them one at a time, then see what variables look good, and then leave the ones that don't look good out, and then see if you can assess them after you put the variables that look okay in the model. That's what you're going to have to do for the take-home final, but that's not what you're going to be doing on this exam. So, and in fact, another thing you're not going to have to worry about on the exam is when showing this output, what I skipped was this code business, the code of how you actually run proc pH reg to actually get out these goodness of fit tests. Statistics, what are called Schoenfeld residuals. I didn't go over this. And for the exam, you're not going to have to worry about whether you're going to get a question on what the code looks like in order to be able to do this. You might get a question. You're very likely to get a question of getting an output and seeing drawing a conclusion about it based on the fact that it's a goodness of fit test. And what conclusion do you draw? But I'm not going to ask anything, so I want to allay whatever fears you may have about, do I have to learn all this computer stuff? Well, you have to learn it at some point, but you don't have to learn it for Thursday's class. But at some point, pretty soon, you're going to have to make sure that you know how to use it. So, and that'll be covered in the lab. Actually, it won't be covered in class, the code business, how to use the code, because we've got a number of other things to keep doing in the class. So it's going to be covered in the lab, but it won't be covered in the lab in tomorrow's lab, because we don't want to spend our time tomorrow's lab when you got a test the next day where this is not going to be on the test. Okay, so anyhow, but this is one of the three options. So we talked about that, and that's sort of where we were at the end of. Now I want to say a couple of other things just before I conclude. You remember I showed you this, or I don't know if you remember I showed you this. This is slide number 22, just so you know where I'm going here. And I showed you this slide, and what it says is the title is Adjusted Log Survival Curves Using pH Reg Remission Data, Males versus Females, Adjusted for Treatment and Log White Blood Cell Count. So what's being graphed here? What's being graphed are what are called adjusted survival curves, okay, where the variables treatment and log white blood cell count are being put in the model, but the variable let's see, adjusted, and this is for sex, the variable sex has not been put in the model, okay? So if you decide that these two variables, treatment and log, are okay, and you want to still check whether the proportional hazard assumption for some other variable, like the sex variable that you're not so sure about, you don't put that variable in the model. You leave it out of the model. So what do you do with that variable? What do you do if you're leaving it out of the model, but you still want to sort of have a graph that compares males and females and adjusts for these other variables? Well, what you have to do is, we talked about that, you have to stratify on the variable that you're leaving out in the model. So that leads to the topic that we're going to spend talking about today, this whole business of what do you do to stratify? How do you go about the business of stratifying on a variable you don't want to put in the model because you want to either check it out to see whether it still doesn't satisfy the assumption or does once you leave it out of the model, or you might even want to decide, if you've made a decision that the variable doesn't belong in the model, to just basically do an analysis where you leave it out of the model and you control for the other variables you think are okay. So that's what's called stratified survival analysis. And when you're using the Cox proportional hazards model to do it, it's called stratified Cox. So that's what we're going to talk about today. Okay, that's what and that's the lead-in into that. Now, in this case, it looks like once you adjust for sex treatment and log white blood count, the sex variable still isn't satisfied. So if these are the only three variables you're dealing with in your analysis, treatment, log white blood cell count, and sex, you're not going to fit a proportional hazards model that includes all those three variables. Because if you do, you're including a variable in the model that's not satisfying the assumption. So what do you do? So that's the next topic. So that's what we're going to start talking about. Okay? Unless you have a question for me about anything I said up to this point. But that's what we're now ready to talk about. Now again, I tell you that even though this is not going to be on the exam, I think it's going to be helpful to you in terms of reviewing what survival analysis is all about, and actually something you need to learn about anyhow. So I guess what I'm trying to say is please pay attention. Yes, this is Rini?
No.
This is Rhonda. Okay, sorry. I can't even see, but anyhow.
Just to clarify on that last graph that we looked at.
The last graph, yeah, which I just took off, but go ahead. Yeah.
The x-axis, is that log of time or?
Well, okay, the x-axis, did it look like the log of time? It might have, I don't remember. Does it say log of time? You've got it in front of you.
It doesn't say log.
Okay, it could be either time or the log of time. It could be either one. And actually, it doesn't really matter what it is in terms of when you look at these log-log curves, how you're going to make a decision. It's going to just sort of scrunch things up a little bit or not, but it really won't really matter. So if that's what you're worried about.
Yeah.
So, okay. So, now let's talk about the stratified Cox procedure. Now, that's what we're going to start doing. Okay. Now, and what we're dealing with here is a situation. There are two situations. One is you have a variable that you know when you try to look at the three approaches for checking the assumption doesn't look like it satisfies the assumption, so you want to do something about it. You want to still account for that variable in the analysis. So that's one main reason. That is the main reason for doing a stratified Cox approach, because you want to somehow do something about that variable and you still want to take it into account, so you stratify on it. Of course, another reason for doing a stratified analysis is you're still checking out that variable. Like if you decided that treatment and log white blood cell count were okay and you wanted to see whether sex should be left out or maybe still could be included given treatment and log white blood cell count are okay, then you might want to use stratified analysis to check out whether you could eliminate, you should really wind up putting that variable in the model or not. So in any case, we're going to sort of now proceed as if we've made a decision that some variables are okay, they belong in the model, and at least one variable, or it could be more than one variable, can't put it in the Cox proportional hazards model because it doesn't satisfy the assumption. Okay, that's what we're going to do. Now, and what we're going to say is, well, what do you do? How do you deal with that? Well, there's actually two options, one of which is the one we're going to talk about today, the stratified Cox approach. The other option is to, again, use what's called an extended Cox model, where you take the variable that doesn't satisfy the assumption, and somehow you actually define a time-dependent variable to put it in the model. That means that the model is no longer a Cox proportional hazards model, it's an extended Cox model. Well, as I said over here, later, that's for later. So we're going to talk about the stratified Cox model now. And we're going to talk about it with two examples, but I'm probably going to spend almost the entire class, because of time, on one example. The example is going to be the remission time data, where there's only one variable we want to stratify on, which turned out to be, for that data set, was the sex variable. And so we're going to talk about what does the model look like, how you use pH-reg to do stratified Cox. We're going to talk about what the output looks like, what the analysis and the interpretation, and then we're going to actually talk about there are two forms of the stratified Cox model. One is called a no-interaction stratified Cox model, and the other is called an interaction stratified Cox model. And to understand the distinction is what I'm going to try to sort of get across to you. This part of this whole part of the course on survival analysis is more difficult than what we've done so far, because as we start getting into variables we're stratifying and variables we're putting in the model, it gets a little bit more mathematically complicated. So I hope you can handle it, and bear with me, and please ask questions of me and the TAs if you have trouble with this thing. Of course, I realize it's hard to do that in a class like this. That's why we have the labs. There is a second example, which is going to be more complicated. It's going to involve more variables that you're stratifying on, and therefore it's a little bit more difficult to figure out what the analysis will look like and how you would do it. So in any case, as I said, as I just sort of previously said, there are two reasons for doing a stratified analysis. One is to evaluate the pH assumption for one or more predictors you're not sure about, and the other is to control for predictors that don't satisfy the assumption. Now, there's a footnote, or I don't know, footnote, there's a note at the bottom of this screen here, which relates to the following situation. In our example, the remission time example, okay, remission time data, we decided, based on when you looked at the log-log curves, that the treatment variable looked like it was okay. Remember the log-log curves for the treatment variable were very parallel, as parallel as you could ever get. Treatment variable looked fine. Now, the treatment variable was your main variable of interest, right? That's, in other words, the goal of the study was to see if the treatment did better than the placebo, and the other variables, log, white blood sugar, and sex, were control variables you wanted to account for, but the main thing you want to look at was the treatment variable, the effect of the treatment. Now, what if it turns out, when you check the proportional hazard assumption, that the treatment variable turns out to be not satisfying the assumption? Treatment variable is like your exposure variable of interest. What if it turns out that variable doesn't satisfy the proportional hazard assumption? Well, if you stratify on it, and you put the other variables in the model that satisfy, but the variable that doesn't satisfy it is the treatment variable, and you stratify on it, what can't you get from the model? In other words, you're using a Cox proportional hazard model, put in the other variables that are okay, but you're leaving the treatment variable out and you're stratifying on it. What won't you be able to get from that model? You won't be able to get a hazard ratio. Remember, the only way to get a hazard ratio from a Cox proportional hazard model is to use an e to the beta formula, where you're looking at the coefficient of any of the variables that are in the model. And if the treatment variable is not in the model, you can't get it. So you got a problem. It's sort of a disadvantage of using stratified Coxes when the exposure variable doesn't satisfy the assumption. Well, you really got a problem as to what to figure out what to do. And stratified Cox is usually not the best approach. That's the usual situation when you wind up using an extended Cox model, almost for sure, because you can't get a hazard ratio if you do a stratified Cox. Now, there is a way to still justify using stratified Cox, but again, you're not going to get a hazard ratio if you do that because you're not putting the variable in the model. Anyhow, that's what the point of the thing is. Now, we already saw that as far as the remission data was concerned, it looked like the sex variable didn't satisfy the assumption. I already spent enough time already saying that it looked like that variable was not appropriate to put in the model, and therefore we would want to stratify on it if we wanted to do an analysis where we wanted to consider that variable. Now, this is Proc Life Test. This is just the code that we'd use if we wanted to see, and we already showed you that picture of the fact that the log-log survivor curves for the two sexes intersected. So that's just, we already saw that. And this is what we got. This is, they intersected for the two sexes. So sex variable doesn't satisfy the assumption. These are the survival curves, these are the log-log curves. Don't put the sex variable in the model. And if you adjust for the two variables that look like they satisfied it, you still don't have a good thing for the sex variable, still shouldn't be put in the model. So what do? You use what's called stratified Cox. Now here's what it is. What you do is, and this is really basically what I've already said, but I'm just writing it down a little bit more specifically. The stratified Cox model, sometimes called the SC model, stratifies on the predictors that don't satisfy the assumption. So if there's only one predictor, and that's the sex variable, you don't put it in the model, you stratify on it. It includes in the model those predictors that you decide are okay, that satisfy the assumption. Variables that don't satisfy it, you leave out. The variables that satisfy, you put in the model. So in a sense, all I've done at the bottom here is just reiterate the fact that you're not putting in the variables that don't satisfy the assumption. In the model, you're stratifying them. So that's basically what it is. Now, what does the model look like? That's the next thing. Now we're getting a little bit more specific, okay? What does the stratified Cox model look like? Well, the model I'm showing you up here is an example of the stratified Cox model, but it's the no interaction version of that model. Now, look at this formula. Is it a survivor function or a hazard function? You know the answer to that. It's a hazard function because you see H, right? And you see H t of x, right? Hazard function of time t for a person who has a set of predictors that are put in bold letters. X refers to x1, x2, say to xp. Now, what's different about what you see in what's written here from what you saw when I first showed you the Cox proportional hazards model? What's different? What's different is there's this subscript here, H sub g. Okay, there's a subscript here. And G stands for whichever stratum you're talking about. So when you're talking about a stratified Cox model, you're saying you have a different hazard function depending upon which stratum you're in. That's what it says. So that model, in order to specify a stratified Cox model, you have to write it H sub g t of x. That's what you have to do. The G has to distinguish the different strata. Now, in this case, how many strata do you have? Well, I just got some notation here. I've said K star. There are K star strata. For the remission time example, what was K star? Well, it's down here. There it is. There's your answer. K star was 2, right? Because there was only one variable, didn't satisfy the assumption. It was the sex variable, and there were 2 strata involved. Okay, so K star is 2. But it may turn out that there are more than 2 strata that you're worried about that you have to worry about stratifying on. Or there may be more than 2 variables. Now, for example, what if it turns out that if sex doesn't satisfy the assumption, and let's add another variable, race and sex. And suppose you have race in 3 categories and sex in 2 categories. How many strata are we talking about? 3 times 2 is 6. Well, that is, we're talking about 6 categories of these 2 variables that don't satisfy the assumption. So what's K star is what I'm trying to say. K star would be 6. Get what I'm saying? K star is the number of categories that correspond to the variables that don't satisfy the assumption. So if there were 2 variables, one of which has 2 categories and the other of which has 3 categories, they don't satisfy it. That gives you 6 categories of you might say, a combined variable that doesn't satisfy the assumption. So K star is the number of categories you get when you consider all the variables that don't satisfy the assumption. And you might say when you start with sex and race, say race in 3 categories, sex in 2 categories, and you combine them and you get 6. You get 6 categories when you combine them together. In a sense, you're defining a new categorical variable that has 6 categories. It's a race-sex combination that has 6 categories. That variable I'm referring to as Z star. That variable is the combination of whatever variables didn't satisfy the assumption. I'm giving it a new name. I'm calling it Z star. I could have called it race-sex if those are the 2 variables. Get what I'm saying? I'm not sure if you are. In any case, that's the model. Now, another thing about this model is this is the left side of the model, but you notice if you look at the right side of the model, there's also a G over here. You see that? There's a G over here. What's the G? Where's the G? It's on the baseline hazard function part of the model, right? So there's a G here, and there's a G for the baseline hazard part of the model. Do you see any G's over here? No. So that's what actually, we'll see this in a minute, this is what makes this model a no interaction stratified model. The fact that even though there's a G over here, there are no G's over here. So let's see what this model looks like by looking at the bottom of the screen, at least as far as the remission time data. So if we're dealing with the variable sex, we're stratifying on sex into two categories, and we put race and log white treatment and log white blood cell count in the model, and we consider what this model looks like for this situation. G goes from K star is 2. So there are two different values that G takes, 1 and 2. Okay, there's two strata. Okay, so we're going to get two different hazard expressions, hazard function part of this formula. H1 T of X and H2 for the two strata. And H1 T of X is going to be H01 of T, and H2 T of X is H02 of T, because these are the two different strata. What about the right-hand side, the exponential part? Well, the exponential part is e to the beta 1 treatment plus beta 2 log white blood cell count for this side, for the males, and the same for the females. But you don't see a G down here in the exponential part. Okay, so what if I said to you, for the males, looking at the formula, this formula for the hazard function just for males, what would you say is the expression for the hazard ratio for the effective treatment, controlling for log white blood cell count, and for males? What's the formula for the hazard ratio for the effective treatment? It's e to the what? Beta 1, right? What's the formula for the hazard ratio for the effective treatment if you're talking about females? It's also e to the beta 1. So what you see is, regardless of whether you're talking about the variable that you stratified, you're getting the same exact hazard ratio. So the hazard ratio is independent of the variable you're stratifying on. So there's no interaction between the variable in the variable, in this case treatment variable, it's also true for log white blood cell. There's no interaction between the variables in the model and the variable you're leaving out of the model. The variables you're leaving out of the model. There's no interaction. The hazard ratio is the same for the treatment variable. It's also the same, it's a different formula, but it's the same for the log white blood cell count variable. It doesn't depend upon the variables you stratify on. That's what makes it a no interaction model. What do you think would make it an interaction model? What do you think you'd have to do to make it an interaction model? Well, you notice that there's no G's over here. So if you wanted to make it an interaction model where the hazard ratios might be different depending upon your male or female, if you put beta 1G and beta 2G, if you put the G in there even on the exponential part of the model, then you're talking about an interaction formula of the stratified Cox model. So one of the things you have to do when you're doing a stratified Cox model, you have to make a decision as to which of these two forms of the model is appropriate. Of course, the no interaction model is easier. It's easier to deal with, it's easier to run and all of that stuff, but it may be that you should have interaction. You should have an interaction strategy. Now, this doesn't mean to say that any of these X's in the model are in product, any of these X's don't involve product terms. You could still have interaction among the variables that satisfy the assumption. They go in the model. You can have product terms among the X's in the model. But as long as there's no interaction between the variables in the model, even if one of them is a product term and the variable you're stratifying on, that's what's called the no interaction model. You have to maybe think about that a little bit. So let's go on with this. Okay, so I already said the stratification variable, you might call it Z star, and if it turns out you identify a whole bunch of variables that don't satisfy the assumption and you categorize each one of them and you get K star combinations, then this Z star variable in a way is a new stratified or categorical variable that involves K star different strata. If it turns out you had sex and race in two categories, making it easier, then Z star would be a 4-category new variable that would combine the two. You'd be stratifying on race and sex or on the variable Z star, which has 4 categories. So 2 ways to say the same thing. Okay, now, let's say a little bit more about the stratified, the no interaction version. As we already saw with the remission time example, that for this general model, you have the same coefficients for each G. So there's no interaction between the variables that are in the model and the variable of variables that you're stratifying on. Now, does that mean, that means that the hazard ratio is the same for each stratum. It doesn't matter whether you're male or female. If you're stratifying on sex and that's the only variable you're stratifying, the hazard ratio is going to be the same, whether you're male or female, in a no interaction model. But does that mean that when you start plotting survival curves, they're all going to be the same for males and females? And the answer is no. Why? Why not? Why are the survival curves still likely to be different, even if the hazard ratios are going to be the same regardless of the variables you're stratifying on? The reason why is because of this part of the model. In other words, this part of the model says the baseline hazard part of the model does depend upon which stratum you're in. And as a result of that, when you actually go from the model to the survival curve that corresponds to the model, you're going to get a different survival curve. So when you talk about a stratified Cox model, even though it's a no interaction model, the survival curves are still going to be different depending upon which strata you're in. So you still have to worry about that a little bit. Again, now I realize you all are here and you're taking the exam on Thursday, so you're starting to say, Jesus, he's going to go on for the rest of this class on this thing. Do I really want to, and the answer is yes. I hate to tell you. The reason why, and why is it yes? Because this is stuff you need to know, and if I don't cover it now and I try to cover it next time, we're not going to get to the end of the course when we want to have a whole bunch of things that we want you to know. So that's why I'm still going to do it, but I'm going to try to make it fun. I don't know if I can do that. And you're not having that much fun, are you? Because you want to take the exam, get it over with. I think that's probably the case. But anyhow, okay, so let's talk. So the likelihood function is even going to be have a special form for the stratified Cox model, but let's not talk about that. Let's talk about a little bit more practical here. Let's look at what's on this screen. Now, what's on this screen, it's code, okay? It's code for how to run the PH-REG program if you were going to do a stratified Cox model. Now, I previously already showed you what the code was if you're just doing a Cox model, but not a stratified Cox model. Now, of course, the beginning part of this code over here has to do with something having to do with plotting the survival curves, which is another thing you're not going to have to do. You're not going to have to worry about for the exam how to plot the adjusted survival curves on the exam. You're not going to have to do that. We can't get you to do that on the exam because you're not going to be using the computer to run these things. But look at the code down here at the bottom. It says proc pH reg. It says model serve T star status. You need to say this in order to tell the computer what the outcome time variable is, what the failure status variable is, and you have to put the variables that you say you decide to satisfy the assumptions in the model. Now, what's different about this code than what we previously showed you is this statement here. See, it says strata sex. So if you want to do a stratified Cox model, you have to add a strata statement, and you have to tell the computer what to put for that statement. And if the only variable that you're stratifying on is sex, and there's only two categories of it, then you say strata sex. That's the key part of what you have to do to run a stratified Cox model. Now, this other stuff, these last two lines have to do with what you would want to do if you wanted to plot the different survivor curves for a stratified Cox model. Now, I'm going to show you what the plots look like, but again, I don't want to go over the code for you because that's going to kill you if I have to go over the code anyhow. And I just want you to get the idea of what's going on. The key thing here is that if you're going to do a stratified Cox model, you have to add a statement which tells the computer what you're stratifying on. Okay, that's the key thing. Okay, now, here's what you get. If you run the stratified Cox model, where sex is not in the model, and you're putting treatment and log white blood cell count in the model. This is the output for this no interaction model. Now, you notice in the output, this looks like the other output we had when we were doing a Cox model. See, you've got two variables, treatment and log white blood cell count. What don't you see on this list? You don't see sex as one of the variables listed as one of the parameters. Why don't you see it? I want to make sure you understand that. Why don't you see the variable sex on this list? Because you haven't put it in the model, and you're not going to get an estimate of the regression coefficient for sex because it's not in the model. You've stratified on it. As long as you've written the code properly, then you're going to get output. Even though this output doesn't have the sex variable in the model, you have controlled for it because you've stratified on it. So you've put the two variables you wanted to put in the model, and you've left the sex variable out, and you've written the code to allow you to do what you want to do, which is control for the variables that satisfy the assumption, and also control for the variable that doesn't, but you leave it out of the model. So in this case, if you got this answer, now you see the 2.537 over here? What's that? What's that? Well, it's in the column that says hazard ratio, so we know it's a hazard ratio. What is it the hazard ratio for? The effective treatment adjusted for, now I want to make sure you understand this, the effective treatment adjusted for what? Log white blood cell count, and, is there an and? It's also adjusted for sex. But sex isn't in the model, it's being controlled for by stratification. So this 2.537 is an adjusted hazard ratio and adjusts for two variables, one of which is in the model and one of which isn't in the model. But you are controlling for both of these variables. Okay, so that's a very important key point, even though this looks like the kind of output you'd get if you weren't stratifying on. But as long as you wrote the code in such a way that you put a strata statement in there, then you actually are controlling for this other variable, you're just not putting it in the model. Okay, you with me on this? Is this the worst thing you ever had to deal with before you had to take an exam? I don't know. It is, probably is. But anyhow, I'm going to keep going. Okay, now this information is a bunch of stuff that has to do with what you might do if you wanted to plot these curves, which I don't want to get into. But I want to show you what the plot looks like, bottom of the screen. Okay, now, you notice, I don't know if you do notice this, but you may not hardly be able to see this. There are four plots. This one is a little bit not that clear because it's a light green. There are four plots. Are they survival plots? Well, because the heading says survival probability. Okay, so it's survival plots. What's being plotted? What's being plotted? There's four plots. Okay, what's being compared? I don't know if you can tell what's being compared. Well, again, the main question of interest is treatment different from placebo, right? That's what you want to know. Is treatment different from placebo? You're putting in treatment in the model. You're also putting in log white blood cell in the model, but you are controlling for sex. So if you think about what you're trying to do here is, these are adjusted survival curves. The word here is adjusted survival curves. You're adjusting for treatment, you're adjusting for log white blood cell count and you're adjusting for sex. The way you're adjusting for log white blood cell count is you're in the model. The way you're accounting for sex is you're stratifying it, like I've already said. That's why you have four curves. For example, two of these curves are comparing treatment with placebo for males. And another two of these curves are comparing treatment and placebo for females. That's why there are four curves. You're adjusting for sex, but you are comparing the treatment, but since you've stratified on sex, you're getting a comparison for males, and you're getting another comparison for females. So that's why you're getting four curves. Now, the thing is, when you look at this graph, you say to yourself or myself, you says, what a mess. I don't really want to look at this. I really want to compare treatment with placebo for males, and I want to compare treatment with placebo for females. So can I do a little better job than just put all four on the graph? Well, there's also a way, and again, I'm not going into the code per se, but there's a way you could write the code so that you wind up getting, and I've said it in a number of different ways, what is this? What am I doing here? How many curves are on this graph? 2. And what does it say at the top? Females. Okay. The next graph, how many graphs? 2. That's for males. So you can either put all four graphs on the same screen, on the same graph, all four survivor curves on the same graph, but that's not really what you'd want to do. You'd really want to put the males separately from the females and compare treatment and placebo for males, and so you can do that. You just have to get comfortable with using the computer to do this. So that's one of the things you're going to be learning between now and the time you do the take-home final. You're going to be learning to be able to plot this thing, to plot them so you can do them separately. And there's going to be a question like on the take-home final, which is going to ask you to do that. Okay, I'm just showing you what you can get, but you're going to have to eventually learn how to do that. So anyhow, now, okay, so look at the model up here. Look at the model I have here on this slide. Just the next slide. Whatever number it is, the next slide. You see what the heading says? Allowing for interaction. Why is it allowing for interaction? I previously showed you what the model was for no interaction. Why is it allowing interaction? Because in addition to the G you see over here, there's a G for each one of these regression coefficients. Previously there wasn't. Okay? So now I'm letting the effect of each variable be different depending upon which stratum you're in. Okay? That's the interaction model. Okay? That's the interaction model. Okay? Now, just to see what the interaction model looks like for the remission time data set, if we now have two strata, where the variable we're stratifying on is sex, and the two variables we're putting in the model is treatment and log white blood cell count, this is what this model will look like for males and females. Can you see that for males and females, again, it's H01 of T, H02 of T. Now it's beta 1, 1 because it's beta 1, G is 1, and then it's beta 1, 2 when G is equal to 2. So these two betas for the treatment are different now. They're not the same because it's an interaction model. And the two betas for the log white blood cell count are different because we're talking about a different coefficient depending on whether you're male or female, depending on which strata you're in. So then if I ask the question, for males, what's the formula for the hazard ratio for the effective treatment for males, adjusted for log white cell count? What's the answer? It's e to the beta 1, 1. The answer for females is not e to the beta 1, 1, it's e to the beta 1, 2. So we're getting a different hazard ratio for males than we are for females in an interaction stratified Cox model. We're stratifying on the sex variable, but we're allowing the effect of sex to be different depending upon the variables that we're putting in the model. So that's the interaction model. Okay. Now, a couple of things. One thing is, there's the interaction model and there's the no interaction model. Now, one thing I've already shown you how to write the code for the no interaction model. I need to spend a little time talking about how to write the code for the interaction model, even though you're not going to have to do it. But let me ask you this: suppose you knew the code, you wrote the code down for the interaction model, and you wrote the code for the no interaction stratified Cox. You had fit those two models. And you got your maximum likelihood estimates for the two models. And you wanted a test of hypothesis. You wanted to decide which model should you use, the interaction or the no interaction model. What would you do? What would you do? How might you do that test? You're comparing two models. What did you do when you did logistic regression and you were comparing two models? You did either a wall test or a likelihood ratio test, right? Now, these two models involve a whole bunch of variables, so you would think if you're going to do anything, it's probably going to be a likelihood ratio test. Right? Got the idea? So that's how you would do the test. You'd fit both of these models, and you do a likelihood ratio test. Okay? What would you compare? What did you do when you're doing logistic regression? You got this minus 2 log L for each of the two models, and what did you do? Subtracted one from the other. I mean, you know that. You know, you already spent enough time learning that, so you know that. So what would you do here? You get minus 2 log L for each of these two models and subtract one from the other. And that would be a likelihood ratio statistic. Okay? That would be a likelihood ratio statistic. Okay? And it would have a chi-square distribution with a certain degrees of freedom. Okay, now it turns out that the degrees of freedom would turn out to be 2, but it's not that clear why it's 2 without further explanation about why it's 2. But that's how you do it. You fit those two models, as long as you know how to run the code for each one of these. I haven't shown you the code for the interaction model. You fit the two models, and then you get the minus 2 log L, subtract one from the other, it'll be a chi-square. And so what if the chi-square is significant? Suppose you do this test, and you find that the chi-square is significant. Which model are you going to use? The interaction or the no interaction? What do you think the null hypothesis is? What's usually the null hypothesis? The simpler thing. What's the simpler thing? No interaction. So if you reject the null hypothesis, what are you going to conclude? That you need the interaction model. And if you don't reject it, you're going to say, okay, I can use the no interaction. That's how it works. Okay. So that's what stratified Cox is all about in terms of, you got these two models. If you want to decide which one to use, you do this test, just like it's a likelihood ratio test. Now, exactly how you fit the thing is an issue. Now, let me show you something. This slide, I need to skip. Because if I try to explain what's on this slide, you're going to go crazy. So I'm skipping it. Boom. Okay. In fact, I'm skipping that one too. I'm going to show you this one. Okay. Now, on this slide, I've actually written the interaction stratified. This is where it's a little tricky. Okay. I've written the interaction stratified Cox model two ways. One way is on the top of this, and the other way is what's at the bottom. Look at what's at the bottom. What's at the bottom of the screen? Does that look like an interaction stratified Cox model for these variables? Well, I already showed you that. That's what it looks like. What is it saying? You have two hazard ratios, right? Two hazard functions, one for males and one for females. And they differ because not only does the baseline hazard have a subscript G, but also the regression coefficients have subscript Gs. So this is one way, and this is the only way I've shown you so far how to write this model. It does tell you, this way of writing it, what you might do to run an interaction stratified Cox model. What does it tell you? Does it tell you something that you could think about if you had to run it? What does it tell you what to do? It says, well, why don't you do this? Why don't you take your data and separate it into males and females? Just do something, how do you do that in the computer? Separate data into males and females. There's something called a by statement. Ever use a by statement? Separates whatever variable you want into the two groups. Use a by statement to separate the males and females. Okay. Then what you do is you run this model with treatment and log white separately for males, and you run it separately for females. And if you do that, you're stratifying on the sex variable, and you're getting two separate models, which is what interaction means. So that's one way to do it. And that's the way that you might say you prefer to do it, because it makes sense. You get what I'm saying? Just separate the data in males and females, and run for males and one for females. And if you had 5 strata, you separate the data into 5 different groups, and you run it for each one. But anyhow, males and females. Okay. Now look at this model. Now this is weird. This one is weird. And this is the one that, you're going to have a little trouble with. Or at least let's see if you have a little trouble with it. And we'll see what's going on. What is this model? Now first of all, you notice this model it's got hg t of x, h0 of g of t, and then it's got e, and you notice it's got 4 variables in this model. 4 variables. How many variables are in this model? 2. There's 4 variables in this model. What are the variables in this model? Treatment, log white blood cell count. What's this variable? Interaction sex times treatment. What's this variable? Sex times log white blood cell count. And then there's a G over here. So what is this? What does the G mean? It means as long as you see the G, it means we are still stratifying on sex. But now we're putting in 4 variables, and we're stratifying on sex. Now, first thing you might say, based on what we learned when we did logistic regression, is there's something wrong with this model. You don't like this model. Something about this model you won't like. You should not like about this model, even though it turns out it's okay. But there's something you wouldn't like about it. You remember when we talked about Hierarchically well formulated? Remember that? HWF? What about that? What do you notice? There's a product term in the model involving sex, but sex isn't in the model on its own, right? So you don't like that, right? Well, you might not like it. You'd say, well, there's something wrong. I don't like this model because it's not, Turns out that even though this doesn't look legitimate, if you fit this model, you're going to get exactly the same answers as you get if you fit this model. So even though it doesn't look right, it is legitimate, even though it's not technically hierarchically well formulated, because you're getting the same answers as this. So there are situations where you can have a model that's not hierarchically well formulated, but it's still okay, as long as it gives you the answer of something that is hierarchically well formulated, which this is. So this model, even though it doesn't look good, is okay. I'm just telling you that. Now you have to believe, I have to prove that to tell you that. So why it's still okay. Okay. Now, here's this model. Okay. Let's put it this way. Let me see what the next slide is. Anyhow. Okay. The next slide is, here's what I've done on this slide. Got all this stuff, and you see what I've put in the red rectangle over here on the slide. Look what's written. It says a model statement, serve status. You see what's written over here? What model am I running? It's that model. That's this model. That's the model I'm telling the computer to run. Okay? So that's how you would tell the computer to run that model. And you notice I still said strata equal to sex. Straight as sex, because it's got a G here, so I have to stratify on sex to run this model. Okay, now, let's look at what happens here. Okay, let's look at this slide first. What did I do here? What did I do on this slide? I'm not sure if you can tell exactly, but you see it says by sex, sort by sex, and then it says run this model. Do you see sex in this model? No. Do you see strata sex? Do you see bi sex? What are we doing here? What's going on here? What is this doing? This is running males and females separately. What's on this slide is running males and females separately. What's on this slide is running them with one model. This is running two separate models. But I'm telling you, this model will give you the same answers as what I would have gotten if I did these two models. Now, in order to do that, I have to convince you of that. Now, I'm going to try to do that before we quit. Now, first of all, here's the output. Here's the output. When I run that model with the four variables, you see treatment, log white blood cell, treatment times sex, log white blood cell times sex. Degrees of freedom parameter estimates. Now, there's a reason why I've got these little brackets over here, and it's got all this output over here. Okay, and it's got the -2 log L and all that stuff for this model. Okay, now let me just tell you this. Now I'm going to click the screen one more time, and notice at the bottom I've just added something to the bottom. I've added something to the bottom of the screen, a hazard ratio formula. A hazard ratio formula for this model for the effective treatment adjusted for sex. Does this look like the right formula? Go back to this model. If this was your model, what's the formula for the hazard ratio for the effective treatment adjusted for sex? Sort of allowing for the fact, even though the model's not hierarchically a formula, I'm telling you it's okay. What would be the formula for the effective treatment? It would be e to the what? Beta 1 plus anything? Why would it be plus something? Because the treatment variable not only appears here, but also appears here. Right? It'd be e to the beta 1 plus beta 1 times sex. That's what it would be. For this model. Okay? That's what it would be. That would be the formula. Okay, so then let me go to this thing. Beta 1 is 0.26672. That's what beta 1 is. And the coefficient of the treatment times sex variable is 1.59231. So I've just written what you get times sex. What do you get for the hazard ratio based on this output? You see that? Okay, now, let me show you something. Now, here's the hazard ratio. Now, what is the formula? What does this hazard ratio turn out to be? What do you get for the hazard ratio if you're dealing with sex equal to 0? I don't remember whether that's males or females. But if sex is equal to 0, doesn't this drop out? And it's e to the what? 0.26672, which turns out to be 1.306. And there it is, right here, 1.306. Well, what if you're talking about sex equal to 1, which is the other value that sex can take? If sex is equal to 1, it's e to the 0.26672 plus 1.59231 times 1. And if we actually do that, and carry it out using a calculator or whatever, it's 6.418. That's what it is. Now, you notice you don't see that here. But what are these two hazard ratios giving you? What are these hazard ratios? The hazard ratios for the effective treatment, if the sex is 0, and the hazard ratio for the effective treatment if sex is equal to 1. Isn't that what you're getting? Those are the two numbers, right? And this says if sex is equal to 0, there's not much going on, but if sex is equal to 1, it's a big effect. Doesn't say that? And you can even get confidence intervals around that. But that's what I'm getting, using this model that doesn't look like it's a legitimate model, I can get two hazard ratios, one for males and one for females for the effective treatment. You with me so far? I don't know if it's not that bad. Really, it's not that bad. Now, here's what happens when you see sex equal to 0 up here, sex equal to 0 up here. This is when I just run the model for the males or whichever one group it is. Let's say it's the male, sex equal to 0. Okay. When I run that model just for sex equal to 0, I separate the data for males. I just run it on males. And I only put in treatment and log ultrasound. I'm not stratifying on anything. I'm just separating it to males and females. I get this coefficient for treatment and this coefficient for, now I go e to the 0.26672. You see the 1.306? That's the same thing we got before with this thing. See the 1.306 we got for this model? This is what we get when we just do it by sex equal to 0, separately. What happens when we do sex equal to 1? Sex equal to 1. Well, these are the two coefficients I get, the two estimated regression coefficients, 1.85904. When I exponentiate that, you see that number, 6.418? See that number? Well, that's the number I got when I plugged in 1 in the original, in the more complicated way of writing the model. So what I've just done, believe it or not, but believe it, that both those models give me exactly the same answers. They give me two hazard ratios, one for males, one for females, and I could write the model one way or the other. Either way. Which way do you want to write it? Doesn't matter. As long as you do it one way or the other. As long as you know what you're doing. Now, let me ask you this. Now, if I look at this model for all four of them there, you see minus 2 log L? You see this 111.670? What's that? That's the log likelihood statistic for that model that allows us to have an interaction model that we know gives us the same answers if we separate it. So there's the 111.670. Now, that's the interaction model. What was the minus 2 log L for the no interaction model? Well, we'd have to find it somewhere. We'd have to go back and search through all this stuff. It was 115.120. That's what it was for the no interaction model. No interaction model. So if you wanted to compare the interaction model to the no interaction model, what would you do? You would subtract one from the other. So let's see what would happen. We subtract. I think I may even have this somewhere here. There, 115.20, 111.67. I subtract one from the other. I get 3.53. And it turns out that I say the degrees of freedom is 2, and that the p-value is not significant. Now, question is, why is the degrees of freedom 2? Well, let's go back to that model. Let's go back to, let's go back to this model. Okay. This is the interaction model. This is one way of writing it. This is the other way of writing it. Okay. Now, how do you go from the interaction model to the no interaction model if you're starting with the interaction model? What do you have to set equal to 0 in the interaction model to get the no interaction model? You'd have to set beta 1, 1 and beta 2, 1 equal to 0, right? If both those two coefficients are equal to 0, equal and equal to 0, you'd get the no interaction model, right? How many coefficients are you setting equal to 0? 2. That's why the degrees of freedom is 2. If you're setting 5 coefficients, degrees of freedom would be 5. That's why it's 2. Okay. Now, you might not be able to figure that out exactly if you were doing this other approach by doing this thing separately, males and females. But here it's easy. So this is one reason why people want to use this approach. Okay, so they like this approach because you can see the two models, and you can see what you have to do to go from one model to the next, as long as you can understand what's going in the model. Now, the thing that I skipped, this one, or this one, I skipped this because this is the most general way you could write that model that allows for, you put everything in one model with all the product terms. This is the most general way you could write it. And if you look at this, you say, God, I hate this. You know, I want to do things separately. So you might, but you notice that you notice I've just, for this thing, I've got this in a rectangle and this in a rectangle. What's this? What's in our remission time? What's X1? What's X1? Treatment. What's X2? Log Y plus L. What's Z1 star times X1? Sex times treatment. What's Z1 star times X2? Sex times like what? So that particular situation that we dealt with is a special case of this. This is just the most general way to do it. Now, some people like this because they like the math part. They want to have a mathematical formula they can use for any situation. And other people won't like it because they don't like the math part. You know, so you have to decide what you want to use. But this is a general way to do it. Okay, so that's sort of the idea here. Now, with all of that, I want to do one other thing. I want to show you this slide. This is how we're going to finish the day. We're going to have, this is a quiz, but you're not getting graded on it. You're getting graded on Thursday, right? You're not getting graded on this thing, okay? Now, but you ought to be able to figure this thing out. This is, you know, and I wonder if you can follow this. This is a quiz. Now, you notice this is my handwriting, which is terrible, you know, okay? So, okay, but it's sort of legible, you know. Now, what I've written on the screen here are 5 models. 5 models, okay? The first model has treatment, log white cell count, and sex in the model. That's model 1. The second model, what is the second model? It puts treatment in log white blood cell count, but it stratifies on sex, right? Third model has treatment in log white cell count and also stratified by sex. What's the difference between model 2 and model 3? One is a no interaction model, that's model 2, and the other is an interaction model, model 3. Can you see that? And you know that model 2 and model 3 are stratified Cox models because you see the G subscript, and because you don't see a G subscript over here, what about model 1? Is that a stratified Cox model? What are you assuming in model 1 that might not be a good idea? That the sex variable satisfies the assumption along with the other 2 variables. So I'm now contrasting 3 models here. Did you follow that? Okay. Now what about model 4? What's model 4? Have you seen model 4? Yeah, we just spent about a half an hour on model 4. Model 4 is the other way to write what I've written for model 3, where you put treatment, log white cell, treatment times sex, and log white blood cell count times sex. The other way. Model 4 and model 3 are the same model, right? They're the same model, they're just 2 different ways of writing it. Okay? You follow that? Okay. Do you feel like you got an idea of what stratified Cox is? Now, what about model 5? Look at model 5. Is that a stratified Cox model? I don't know if you can see it all. Model 5. But you see it says HT. Do you see a G subscript? You see a G subscript? So what are you assuming about model 5? Everything you put in model 5 satisfies the proportional hazard assumption, including treatment times sex and log white plus. You've got interaction terms, and you're assuming, and you've got sex in the model. You assume every variable satisfies the assumption. Now, based on the data, model 1 and model 5 are no good if we decide sex didn't satisfy the assumption. Okay, and also based on the data, it looks like based on the test where it looks like the interaction model was not significant, it looks like model 2 is better than model 3 or 4. So that's our best model. Did you pass the test? Well, it's not over yet, okay, because I still got a couple of minutes here. Now look at this picture. Are we having fun now? I don't know if we're having fun. No, you're not having fun, but I'm putting you through this anyhow. Okay, look at what do I have here on this slide? You see it's got time, and what's LLS of t stand for? Log survival curves. What do you want them to be in order for the proportional hazard assumption to be satisfied? Parallel. Are they parallel here? They're parallel. It doesn't matter whether you're male or female or you're placebo or treatment, everything's parallel, right? What model does this conform to? Which one of these 5 models does this conform to? 1, 2, 3, 4, and 5. Is it 2 or 3 or 4? Well, if it was 2, 3, or 4 when sex didn't satisfy the assumption, then these things couldn't be parallel. So it's model 1. Okay. Now look at this graph and look at this graph. Look at this one and this one. What's this one doing? First of all, you notice, this is a good quiz. This is a fun quiz. Well, you don't believe it, but this is fun. Look how does this differ from this one? Is everything parallel? Yeah. Well, how does this differ from this? Well, the difference between treatment and placebo for males is a lot more than the difference between treatment and placebo for females. What does that mean? Interaction between the effect of treatment and the sex variable, right? What model has that? When everything's parallel. That was model 5, right? Got it? Okay. So now, we're not done. Let's look at this. Look at this one. And look at this one. This one versus this one. Those are the only 2 left. Which one is this and which one is this? Is this a no interaction are these 2 stratified Cox models? How do you know they're stratified Cox models? Because they're not parallel for sex. These 2 aren't parallel to these 2 either way. This is going one way and this is going the other way. So they're not, the log curves aren't parallel when you talk about the sex variable, right? Am I pulling the wool over you here or what? So both of these are stratified Cox model. Which is an interaction stratified Cox model and which isn't? Well, I've pretty much given it away when I compared these 2. Which one is an interaction stratified Cox model? This one, because the difference here is bigger than the difference here, right? So which model is which? Is this model 2? Or model 3 or 4? This is model 2. Which model is this? 3 or 4? You got it? Okay, so we're done. Have fun on Thursday. I hope you learned something today, even though you didn't want to be here. You really didn't want to be here, but, I forced it. Okay? And I'll stay around if you have any questions.